An exposed piece of modern iron rapidly corrodes in the rain. Within a few decades, it crumbles into orange flakes. Yet, a specific artifact in India, forged 1600 years ago, is completely defying that chemistry. We usually assume technological progress moves in a strictly straight line, starting with primitive tools and arriving at modern industry. Because of that assumption, early historians often looked at the complex texts and massive stone structures of ancient India and categorized them as purely religious art or colorful mythology. But modern science forces a different perspective. These artifacts may actually be the surviving fingerprints of a highly organized technical society. By examining 4 distinct ancient marvels, we can reconstruct the actual engineering blueprint used to maintain this ancient knowledge hub. Take the Iron Pillar of Delhi, located in the middle of the Qutub complex. It was forged during the Gupta Empire over 1600 years ago. The core anomaly is right on its surface. Despite sitting outdoors and taking the brunt of heavy monsoon rains and humid air for centuries, the iron lacks any significant rust. Metallurgical analysis reveals that these ancient smiths forged a specific protective film over the metal. It is a layer of iron hydrogen phosphate, a complex chemical compound that actively prevents corrosion. As water and oxygen molecules hit this iron hydrogen phosphate barrier, they bounce off. The chemical layer neutralizes the exact environmental elements that cause raw iron to decay. Formulating a highly specific chemical shield requires deliberate, advanced knowledge of metallurgy. It is a calculated technical achievement. A large-scale civilization requires a massive geographic engine to support its population. The Rig Veda, one of the oldest texts in the world, frequently references a massive, powerful waterway called the Saraswati River. For generations, historians could not locate it on any map, leading them to classify the Saraswati as a mythological fairy tale. That changed when scientists pointed satellite imaging technology and deep geological surveys at the arid deserts of northwestern India. When they peered directly beneath the modern sand, they found a massive network of dried ancient riverbed channels. The physical geography matches the detailed descriptions in the ancient texts. Validating the physical existence of the Saraswati River suggests that the Indus Valley civilization developed directly alongside this massive, now lost hydrological network. This society also applied technical precision directly to their public and cultural spaces. We see this at the Brihadiswarar temple. The interior halls function as precision acoustic environments. They are shaped specifically to catch and amplify the sound of human chanting. At the Vitala temple, the builders carved specific stone pillars to act as physical instruments, producing distinct, clear musical notes when tapped. This phenomenon relies on strict physical principles. It requires exact architectural alignment and a masterful understanding of material resonance to force solid granite to carry specific sound waves. Constructing resonant structures out of solid rock requires a mathematical grasp of physics and sound waves centuries before the birth of modern acoustics. To maintain advanced chemistry, massive hydrology, and precise physics, a civilization needs a permanent institutional framework. Nalanda University provided that foundation. Founded around the 5th century CE, Nalanda operated as one of the world's first residential universities. At its peak, it housed 10,000 students and a faculty of 2,000 teachers in a single location. It acted as a global magnet for the brightest minds of the era. Elite scholars, like the Chinese traveler Xuanzang, journeyed from across China, Tibet, Korea, and Southeast Asia to study its curriculum. Nalanda served as the scalable engine of this society. It actively collected and distributed scientific advancements, establishing the institutional framework that allowed India to export its specialized curriculum across the continent. That massive accumulation of data met a tragic end. When Nalanda was destroyed, its central library was so large the manuscripts burned for months. That fire created a catastrophic vacuum. It erased the formulas, the equations, and the literal instruction manuals of a highly technical society. What we are left with today are the physical remnants: the rust-proof pillar in Delhi, the deep channels of the Saraswati riverbed, and the resonant temple pillars survive as the remaining components of a single, cohesive system. These structures and artifacts suggest a society built on consistent empirical observation and technical precision. By pairing those ancient texts with modern tools like chemical analysis and satellite imagery, we are finally translating the lost technological language of a forgotten superpower.